WCAPP stands for the Wootton Center for Astrophysical Plasma Properties. The center was born from the mind of Alan Wootton. Our goal is to measure in the laboratory material properties such as the opacity of matter at the actual conditions found in the cosmos.
We measure things nobody's ever measured before. We're able, because of the Z machine here at Sandia, the NIF facility, National Ignition Facility, we're able to do experiments that are at parameter, under cosmic conditions, for the first time in the history of astronomy.
There's an experiment we run on the Z machine at Sandia National Labs, which is recreating the photospheres of white dwarfs in the lab. So the actual temperatures and the actual densities at a white dwarf photosphere. And then we measure the spectrum from it from a distance of a few centimeters instead of a distance of many light years as we would for an astronomical object.
We were saying, well, let's look at the age of the oldest stars and see how old they are by the rate they're cooling now. It's kind of the very first calculation you do in differential equations is a cooling equation. So it's a very simple concept, and it yields a limit on the age of the universe itself. So it became important to either validate or invalidate cooling theory of white dwarf stars, because it's the real best cosmic chronometer. Now we're beginning to understand some of the models we had about how they work are wrong, because we pushed the physics too hard. We pushed it way outside the domain of human experience. So we're bringing part of what we do here. These conditions are pretty exotic by Earth standards, but Earth is pretty exotic by the universe's standards. These conditions are occurring everywhere in the universe, and now for the first time we can reproduce them on the surface of the Earth at these laboratories.
The Z machine is about the size of half a football field. It has 36 generators on the outer ring, and those are immersed in somewhere between 500,000 and 1 million gallons of transformer oil. And those charge up, and then all at once they release their charge down into the central vacuum chamber, which is where we have all our experiments arranged. And in a very, very short amount of time, about 2 nanoseconds, it releases around 2 megajoules of energy. It's also nice being connected to the university and being connected to the folks there who are involved in astronomy and not just laboratory astrophysics. I think helps us make the connection between the laboratory astrophysics and the questions that we actually care about in astronomy.
The timescales that we see in these experiments and the timescales that I'm usually worried about when I'm doing my atomic calculations are usually incredibly, incredibly small. But then these are shaping the radiation transfer in these stars that are billions of years old. And so you're really spanning the full range of timescales that are even really physically possible or physically relevant in the universe. I think one of the things that WCAPP and Don and all of my advisors have really impressed on me over these last few years is just how powerful it is to have this connection between theory and observation and experiment.
I was seeing what WCAPP was doing with their opacity experiments and all those sorts of things with stars, and it was an interesting way of thinking about things, but they were also starting to see the work that I was really interested in, which is what are the physical processes that allow the Earth to retain water during violent planetary forming processes like giant impacts and those sorts of things. It turns out that there are these white dwarfs that are showing these signatures of different atomic species, so things like sulfur and iron and different atoms that shouldn't show up in their spectra based on basically the gravity of these really dense stars. And so the idea is that what's happening is in these planetary systems, as they're basically dying and collapsing down, you're actually accreting on planetary material onto the surfaces of these stars. And so this is the only way that we can actually directly sample the interiors of planets.
I'm working on trying to improve models that describe the behavior of atoms in dense plasmas. In these dense plasmas, the structure and behavior of atoms is different than what you would see in your ordinary textbooks. It's very different. You get a lot of line broadening, you have continuum lowering, and my job is to try to better model that phenomena, the dense plasma part of the atomic behavior in those systems. One thing that I really appreciate about the center is that we are moving forward on both theory and experiment. We've got a number of people doing things in the laboratory, and that's really exciting. but you only make scientific progress when you have theory and experiment together.
The fact that this collaboration that we have in WCAPP, different from other laboratory astrophysics efforts, is a collaboration that is emphasizing primarily the atomic physics of the plasma, the atomic processes going on in these type of plasmas. We have an emphasis on atomic processes in this collaboration.
We explore these conditions that we find in the cosmos, the cosmically normal conditions, as Greg Rockow likes to say. We realize that we're looking at something no one on Earth or anywhere has ever understood before, ever seen before. We're creating conditions that are unknown. And so you learn something about the universe that no human being that's ever lived before has ever known. And that is an intoxicating and addicting thing. Makes science fun.